Welcome to the Kielder Observatory podcast for this latest episode, where we come to you from Durham University, and we are in the office of Professor Danny Donoghue, who is going to talk to us about how research from space really can affect our lives down here on Earth, and some interesting information from satellites, not just recently, but from years and if not decades ago, that is still being used today to help further our knowledge of the planet and make life better for ourselves down here on Earth. Now, Professor Danny Donoghue is with myself, Ian Brannan, Dan Pye, Director of Astronomy, Ellie MacDonald, Science Communicator from Kielder Observatory, with us as well. Danny, thanks for joining us. Your work is a fascinating topic. Just start by talking to us first about satellites, the information that you have, the satellites that you've been working with, and as I say, some of these satellites may not be with us anymore in orbit, shall we say, and so this is sort of legacy information, and how you are working with that information to improve our lives and knowledge of the planet here on Earth.
Yes, well, thank you very much. Well, satellites have been looking down at our planet since 1960, the very first time that we gathered images from the Earth's surface. In fact, the very first satellite that was used for what we call Earth resources remote sensing, in other words, a civilian satellite, was launched in 1972. It was called Landsat, and that program has been running right up to the present day. Now, there are many more different satellites that have been launched in the intervening time, and they're used for a wide range of applications. I'm a geographer, so we're interested in looking at the Earth's resources, but satellites are also used by geologists, by oceanographers, and of course by meteorologists, that we rely on satellite technology all the time to provide up-to-date and efficient, effective weather forecasting.
Tell us a little bit about the declassified data from the 60s and 70s then. I imagine that as like some kind of like James Bond like kind of tech from the early 60s of surveillance. But yeah, tell us a little bit more about that.
Yeah, so at the end, if you like, in the height of the Cold War, when things like spy planes were shot down, Gary Powers was shot down. The American Air Force and the CIA got together to think about, well, how do we actually continue to monitor what's happening effectively in the Soviet Union? And they built a program called Corona, which was a series of satellites. And it wasn't until, although the program started in 1958, it wasn't until 1960 they successfully managed to launch a satellite that actually took images and retrieved the film back to Earth. So it was very much like James Bond, as you put it, or actually Ice Station Zebra, if you've seen the Alistair MacLean film, where Kodak were tasked with how do they develop a technology that actually records film without that film being degassed. So they've developed plastic film as a result of that entire program. And of course, the satellite had to be designed with a particular orbit pattern to make sure that it has, if you like, the highest possible resolution over the parts of the world they're most interested in, but it was high enough up so that it couldn't be detected. And then that capsules of film were literally dropped from the satellite and recovered with a net on the back of a C-130 aircraft. So it was very much, if you like, very much in the world of espionage. But a lot of data was collected at that time, not just over the Soviet Union, but over many parts of the world. And it was both covering a large area, but also at high resolution, because effectively it was designed for looking at what, shall we say this, if like the other side were doing. And so that data was declassified actually by the Clinton administration. And that film was made available, and it's now, a lot of it has now been digitized. And over the years, that program developed better and better resolution as they actually started to evolve this in real time. So every single time they launched a satellite, it was better than the last one. So you actually have to have quite a knowledge of which missions were successful and which were not successful. And one of my PhD students, Dr. Nicholas Gelliot-Satos, came to me and wanted to do some doctoral work on this, particularly in the field of archaeology, to be able to look at what landscapes looked like in the 1970s before you had agricultural intensification. And it turns out to be a superb resource, particularly in the Middle East, where you can actually look at sites that are no longer with us. They've either been flooded by dams, particularly in the Euphrates river systems, but also they've been obliterated by modern agriculture. And now some of my colleagues are using it for looking at what's happening at glacial change, where they want to have a long record of what's our shrinking glaciers on the planet. And we're also using it now for looking at what's happening with environmental change in the Arctic, in the high Arctic, to be able to get an understanding of with a warming climate, are we actually seeing vegetation, and particularly forest vegetation, creeping northwards as a result of this. And for that, we need a long record, and this is a particularly valuable resource.
I love the idea of films being dropped from satellites. That just it sounds crazy. There must have been so many complexities in that, not just trying to catch it, but also dealing with it moving through the atmosphere. Because what kind of altitude would that satellite have been at?
Yes, well, so they're actually relatively low Earth orbit, and sometimes not necessarily a circular orbit, maybe an oblique orbit, where the satellite was designed so that it could come very close to the Earth's surface. So certainly less than 100 kilometers, so actually quite low. And particularly over the Middle East, some of the resolution is actually better than, if you like, advertised, because they really were coming close. And that, because these were film, and not all were successful, actually, because things go wrong, like your film gets torn or it actually drops into the sea. And believe it or not, they were in buckets, in sort of salt buckets, so that if they weren't recovered, they would dissolve and the film would be destroyed. It wouldn't fall into the hands of the opposition, so to speak. So it was quite exciting. But the advantage of these films is that, particularly as they developed them through the 1970s, they got better and better, and the optics got better and better. And we were very fortunate to meet one of the photogrammetrists that worked for the CIA, and he was a scientist, not a spy. But because the project was classified, he was never able to talk about this his entire life until the declassification happened, and a couple of papers and a book was published. And then we got together with him and we actually understood a little bit more about what was going on and how best to process the data. And as I say, my colleague did a very good PhD on this, and that helped us to understand how to process this data effectively. And so it is a useful resource. It doesn't cover the entire world, and there was an agreement that the US would not spy on its allies. So thankfully there's actually some imagery from the UK, but very little. Yeah. They didn't do too much spying on us.
It's declassified now, but what was the purpose of the information and the images in the first place? Then, who particularly were they looking at? What was the original intention of these missions?
Yes. Okay. So as I mentioned, I have two PhD students at the moment. They're looking at what's happening in the Arctic. But if you go and look at the distribution of where images were taken, if you go up to places like the Kola Peninsula and Murmansk, where the Soviet submarine bases are, that's exactly what they were looking for. In fact, some of these images are so detailed. It's American, so that effectively the digitization, if you like, the pixel size is something like 9 inches. So it's pretty high resolution. So it's good enough to see individual people. It's certainly good enough to see things like surface-to-air missile sites. It's certainly good enough to be able to detect submarines and be able to tell what type they are and so on. I stress to say that's not my work, but there's a large community of researchers now that we've sort of published papers on this. The archaeological community are very used to using this data, and in fact they've started to make maps. One of my other PhD students did a project looking at ancient water resources things like irrigation canals, effectively from the Bronze Age and from the Iron Age, and it was able to reconstruct the entire network of what was happening and the management of these systems using this kind of data, where you could really begin to see exactly what these were for, and there are a range of projects that these are being used for throughout the world.
I mean, it's amazing that they were getting that sort of resolution, even very early on, I suppose, in a field. Has that improved significantly since? I mean, how much more can you really particularly improve on that?
I mean, clearly these missions have continued right up to the present date. There's these missions which are not declassified. There are a few hints actually as to what the capabilities are. When Donald Trump was president of the US, he accidentally tweeted an image of it was an Iranian missile launch. So we do know, if you like, pretty much what the capabilities of the are. So the original images were black and white. They were panchromatic. They were also stereoscopic, so that you could tell, if you like, you could identify even people from shadows and things. The modern images are likely to be multispectral. There'll be color images. That they'll almost certainly be at the, if you like, like a telescope, essentially, like a space telescope, but looking down. So you can sort of think of something a little bit like a Hubble space telescope as a sort of frame, but part of that sort of mission looking down. But we don't have access to that data. But of course, we now have very high resolution satellites down to 30 centimeters at the moment, which is pretty good. And there are talk of improving that. And our physics colleagues and engineers colleagues really thinking of ways to do that. And they are available for the civilian market, although they're relatively expensive.
So potentially even better now classified stuff that you might get your hands on in the future.
Yes, but it's really the thing that's interesting to us is to be able to work out what was happening in the past, because we're very concerned about how our planet is changing. And there are many threats from, it might be sort of things like coastal erosion, landslides, flooding, and so on. So, but very often we don't necessarily have a record of what the site was like before. And so being able to go into and look at the past situation is very helpful. But when we're thinking about things like, say, 30 centimeter resolution commercial imagery, that's not quite even as good as the 9 inches that I was referring to. So because those data were based effectively on chemistry rather than digital optics, it's taken until now really to get something equivalent, which is interesting.
And from this information then that you have now, and in a way, obviously looking back in time, often with these images, especially the ones from the 50, 60 years ago, maybe now, what are the key things you're noticing about the state of the Earth? We hear a lot about climate change. We hear a lot about how the world is changing. But what are the common themes now?
One good example of this would be to look at the world's largest mangrove forest, which is called the Sundarbans, which is on the, if you like, the edge of the Ganges, sort of Brahmaputra river system and so on, and that spans both Bangladesh and parts of India. And when you look at the Sundarbans from space, from the past and from today, they don't look very different. But it's not until you quantify what's there, you look very carefully at the extent of that forest in the past, and then you measure it today, and you realize actually there has been quite considerable changes. And then what we can also find from the high resolution data is we can tell a little bit about the type of these mangrove forests. So in the past, they were essentially large trees. It's a very diverse forest with many species, but today they've been severely degraded. So the mangrove forests are important because they actually are one of the largest in terms of different ecosystems. They store a huge amount of carbon, both within what's happening above ground, but also below ground. And as soon as they're disturbed, they have they lose that carbon. And it's a part of the Earth system that we really don't fully understand. And using both modern and historic satellite data gives us important insights into that process. So we're currently working, we've done a lot of work in the Sundarbans, and now we're moving into looking at with a new project, looking at what's happening on the Caribbean coast of South America, where again there are important mangrove forests that we see are rapidly changing. We want to understand that with one of my colleagues just started a project called Enhances, and that's partly funded by DFID, and so Dr. Isabella Bavolo is coordinating that project and is helping to sort of gather scientists from Suriname and also from Guyana to help understand these processes.
And from that, what happens as a result of the research that you're doing? Does this get fed back to governments? Does it get fed back to other agencies? So really this information from space, then after you've analysed it and learnt more about it, then what happens?
Yes, that's a really good question. So sort of early on in my career, we were really thinking about the science primarily and partly the technology, how we could use different types of satellite data, how we could use them together, how we could get better information. But as you imply, it's all very well gathering data, but is it used in a practical, beneficial way? So one of the applications of that is we were involved about, it's now 13 years ago, to assist with the government of Guyana, which is at that stage had one of the world's most intact tropical forests. So Guyana is on if you like, the north edge of the Amazon rainforest. So it's actually got about 80% of the country has got still intact tropical forests. So it's very important to conserve these places, because they're effectively drawing down carbon dioxide from the atmosphere and fixing those as wood. And the work that we've been able to do has been helped to independently verify the resource and what's there. And that then feeds into the United Nations program called RED, which stands for Reducing Emissions for the Avoidance of Deforestation and Forest Degradation. And that process is a way in which, if you like, developed countries, in the case of Guyana, it was the Kingdom of Norway, first invested in this to actually try to reduce and to stop deforestation in that country by providing a resource to do so. But in order to do that, they need to have independent verification of what the forest resources are. And satellite technology is, believe me, it's the only way to do this, because Guyana is about the size of Great Britain, so England, Scotland, Wales. It's 21 million hectares. It would be impossible to map it on an annual basis any other way other than satellite data. And there are parts of the country that are impossible to visit, and the only way to get there would be by river or canoe, and even then it would be largely impossible. So field mapping is almost impossible, although there's some validation, but satellites are the only way to do this. So that's nice to be able to see science, if you like, being transferred into something that is really helping one of the key drivers to avoid one of the principal concerns over climate change, which is deforestation. Much
of what we talked about has been relating to, I guess, photographic views of the Earth from space. What about other spectrums then? Do we have data from other forms of satellite?
There's a nice sort of, if you like, link to Kielder Observatory, I think, in some of our early work, where we did a project called Forest Safe, which was funded by, when we were part of the EU, it's funded by the EU Life Environment Programme. And we teamed up with the Swedish Forest Authority, the Forestry Commission in the UK, some of the forest districts in Sweden, and Galloway and Kielder forest districts here. And one of the really interesting technologies that was being really promoted in Sweden was the use of lasers to make remote sensing measurements. these were at the time all based on aircraft. So it was called laser scanning. So essentially, instead of taking pictures, you would have an aircraft that was able to project a single laser beam and then scan it across the surface at very high rates and give you a precise height measurement, so that not only did we could take pictures of our forest resources, but we could measure the height of the trees to a high degree of accuracy. And so that was a really nice example of how you can, if you like, start to look at other aspects, other characteristics of remote sensing. So we may talk in a minute about the different spectral bands, but here we were using particularly infrared lasers that were actually sensitive to the vegetation as well. So there was a colour, but there was also a height. And what's interesting is that work developed relatively quickly, and the technologies have been adopted by industry, and so that many forest companies now routinely do a lot of their measurements of looking at how trees are growing and how successful they are using laser scanning, and that's particularly true in Norway and Sweden, where it's pretty much routine, but it's largely coming into the UK as well. But it takes a while sometimes for the technologies to be adapted. But in terms of space, although we didn't develop this in the UK, there have been quite a lot of interest in putting lasers into space, and there's now, of course, it would be called the JEDI mission, because it's which is a NASA-funded mission that was put onto the International Space Station. So it has a limitation as to how far north it goes, which is a pity for our stuff in the Arctic. It doesn't get that far north, but that's an example where, again, for tropical forests, we can now tell a little bit about the height of the trees by combining that with the optical images, which shows us the extent. So we can see not only if we've lost forests, we can see not only the area we've lost, but the type of forest and the maturity of the forest that's in that area. A good example of us being interested in the spectral characteristics. So if we think about a traditional sort of red, green, blue image of traditional colour, in the range that our eyes are sensitive to, so essentially within the sort of 0.4 to 0.7 micrometer region, the remote sensing technology can both go to shorter wavelengths, as astronomy does, into the ultraviolet, and of course the longer wavelengths into the reflected infrared and even into the emitted infrared, and beyond that even into microwave wavelengths and so on. So we have a whole range of wavelengths we can look at, and that the characteristics of the resources, I mean, if I'm thinking about forestry or vegetation in particular, it's very helpful because plants are very reflective in particularly the near infrared wavelengths. So, if we were to look out the window and see lots of green vegetation, if our eyes were sensitive into the infrared, we would be looking out and saying, what a nice infrared day it is today. So that capability is also very helpful when we're looking at things like plant stress, because those very subtle changes show up first at those wavelengths. So we had a very nice project we just finished with one of my colleagues, Professor Alistair Jump at the University of Stirling, who is a dendroecologist. And he's particularly interested in the decline and the impact of both heat and drought, water stress on trees. And we were looking at European beech, which is the most important commercial tree species in Europe. And for that, what we wanted to be able to see is if we could, first of all, detect stress, and we had some severe droughts during just before the project and afterwards, and we were then able to look at the impact of those droughts and how they manifest themselves in the imagery. And then what he was then doing was, if you like, linking. We could go back in time with our satellite data and see what happened in previous droughts. And he would link that to the dendro data, if you like, looking at the tree rings and looking at the growth characteristics to see if actually we can marry up what's happening with our current observations with what's happened in the past, what the impact has been. Because there's a lot of concern with climate change that a lot of our species may not be able to adapt to climate change. So we might be able to see, severe mortality in some of our species because they're not well adapted to either very warm summers or periods of very intense heating or very intense long droughts. So that's a really interesting example of where the spectral characteristics really help us to be able to link the process of what's happening in the plant with how it behaves when we see it through electromagnetic radiation, through light.
Just while you were talking there as well, I was thinking just about animals and how useful this would be to understand different species movements and how that's changed over time. But also I bet there's some cracking images of stuff which has now gone extinct. I'm thinking like there's certain species of rhinos which possibly would have been around on that film and now they're not. And they must be amazing things to see. I don't know if you know anything about any extinct species that have been caught on film from there.
No, I don't. Not really species, because we're never really, apart from even very high resolution data, it's really still very hard to see kind of individuals, or particularly if they're moving. But maybe one way of answering that is one of my recent PhD students, Dr. Rusa David, who was from Namibia. She's now actually a lecturer at the University of Kiel. And she did her project in an area that borders Botswana, Namibia, Angola, Zimbabwe, and Zambia. And it's a very important area because the ecology supports things like large elephant populations, and zebra, and a whole range of different species. And there is concern that particular part of the world, which we often think as sort of dry forests, so that's much further south from the Congo Basin, where the rainforest, but there's still significant tree populations, and they're important habitat for things like elephant. And there is a real question as to the impact. They've had very severe droughts, and what Rusa's project was using remote sensing to be able to track the changes in the vegetation that those species actually depend on for their livelihood. So effectively, if you're starting to see huge drought impacts, then those populations will either shift to a new location, or they'll move into areas that are unprotected, and therefore they'll be poached very, very rapidly. So it's an interesting area in which remote sensing can really help the management of things like game reserves. And so the CASA one is interesting because it's a cooperation between many different countries, and it's about the size of France. And again, the only way to monitor the vegetation in that area is from remote sensing. And part of the what's really interesting here is to be able to train enough people so that they're able to use the technology and not just dependent on the occasional PhD student or an academic from Durham. That's not much use. What we need to do is embed that technology into their practice. So there was some interesting work done there to work with things like WWF. So they were very interested in this work, and I hope that Rusa will take that forward with. She's a young lady with tremendous ability, and that's what we need in the future. So that's also an important aspect of my job, I think, is to try to encourage other people to see the benefits of this technology and take it forward in their own careers, because you never know where this would lead. I never thought at the start of my career there'd be something that would help, if you like, game reserves in Africa. That wasn't ever anything I thought about, but you can see how that is a very helpful technology.
Obviously, you're dealing with a very specific area here and using information from space, but we know from other previous conversations there is a strong, I guess, what you call space community at Durham University as well, with different departments all contributing in different ways from the work you're doing, but also involvement in things as recent as the James Webb Space Telescope as well. So you do have a community of academics here at Durham University who all have a vested interest in space and satellites and work in the space area.
We do, and that's a very important part of science, is not to be working in isolation. And remote sensing as a subject is very multidisciplinary. So when we look at the academic journals, there even in the application of the technology, there are people from physics and chemistry and bioscience and earth science and so on, and geographers and physicists and so on, all contributing. But so at Durham, we have a number of ways in which we try to get together. We have an Institute for Data Science, which is a great way of trying to think about how a lot of the benefits in data processing and large data sets that are, for example, our physics department or our computer science department are experts in, can be applied to things like geographers or earth scientists that may be sort of less familiar with processing very large data sets. So that's one way we can get together. But it also is an opportunity to get together to think about the science and technology. Can we do things better? And we're lucky enough at Durham, we have a Centre for Advanced Instrumentation in our physics department. They traditionally build things for telescopes, and you mentioned James Webb and so on. So new technology. So we have I've had a grant in the past with Professor Ray Sharples from the physics department, where we've built a spectrometer, and to see whether that particular spectrometer can be used for looking at very dark objects on the Earth's surface. So when we haven't got much light, which is a classic problem in astronomy, but it's also a problem where we're looking at the Earth's surface. We're looking at dark things like oceans are actually dark. They don't reflect a lot of light. So if we want information from those places, or even forests are actually very dark objects. And so that's been really interesting to see how we can work with our colleagues there. There are also opportunities, I think, to work with some of the sort of organisations, if you like, in Northeast England. We have a thing called Space Northeast England, which is part of the UK Space Agency accelerator funding, and that is a way in which we can get together. We have there's a conference every year that's organised by that body, and we worked with our partner universities for PhD training, for example. We share that sort of thing, and I've also worked on a disaster management project with Professor John Mills at University of Newcastle recently, with UK Space Agency funding. So this, and he's from an engineering department. So we're very used to trying our very best to get knowledge and to share knowledge across our disciplinary boundaries.
I do think that if there was more interdisciplinary work between sciences and between just generally areas of research, that we'd get an awful lot more done. I mean, I can think off the top of my head several stories of, when people were just talking, you meet someone on a plane, you're talking to them about an issue that you're having at work, and someone turns around and goes, "Oh, this is the solution. Do you not know that's the solution? We do that regularly in what I do every day." And I wish at conferences there were more sort of general conferences. I think that we'd get an awful lot more work done as a society if you sort of turned up and you said, "Oh, I'm going to talk to someone from, English literature. I'm going to talk to someone who studies chemistry," and, we might find that we've got a lot more in common, or that we can help each other out a lot more.
Yes, no, I agree. And I think that's one of the problems is that we're teaching a degree or degrees in our particular department. So it is there's a danger. You get very focused on just your own discipline. And that's where the institutes that we have, which are by their very nature have to be interdisciplinary, and many of them are across faculties. They have to. So our Institute for Data Science is something where we have many really exciting projects that are in the arts and humanities and music and things like that, as well as things in sort of in the more tech sphere of chemistry, physics, computer science, and so on. But when we do get together, and occasionally we have these what we call in-reach days, where we look at what different people are doing, and very often it's that, oh, I really never thought of that. You're really actually going into this and challenging yourself, and so that's really exciting, and we need to do more of that actually, because they do say that there are going to be very few people that graduate from universities that will end up in a single job for all of their careers. So they will certainly not be like me, even though I did start off my career actually working in with industry, and I've sort of almost sort of finished it as well, doing some interesting projects with industry, and I think that's really helpful because it allows you to see the practical side of it.
You should definitely try to get an astronomer on board just to help with particularly actually naming. Astronomers love to name a mission.
Yes.
Give you the most mind-boggling acronym that reduces to something stupid.
No, absolutely. Actually, we're probably really bad at that kind of thing. And when I started my career, I actually did my sort of first sabbatical period. Actually, I spent some time at NASA Jet Propulsion Lab, and they're fantastic at naming stuff. It's great, and of course they're really great at involving the public. So I think we probably have a lot to learn from that. So the idea of podcasts and things, of getting things out to a wider audience, I think is really important actually, because they have people coming in, and sometimes people ask the daftest questions, which makes you think, oh wow, gosh, we never thought of that. So that's exciting, and then. Obviously, part of that is actually trying to then, if you've got a good name and a good link, it's a good way to encourage things like school children to think, well, actually, this sounds like an interesting discipline. Mm-hmm. This could be fun, which is important, yeah, because it's one thing I say to my first year students, actually, there will be people, some of you out there, you don't know it yet, you're going to have a big impact. Mm. You really are, but you don't know because you don't know what knowledge you're going to gain. It's going to be fun.
You definitely need to get more 7-year-olds, I think, on board, because they, in our experience of doing this podcast, it's always the 7 or 8-year-olds that ask the questions that the astronomers and so on, and the academics can't answer.
Well, that's right. That's the Groucho Marx line, isn't it? Where somebody said, look, a 7-year-old child would be able to answer this, and he said, well, go find me a 7-year-old child then.
Just to touch on another technology, we talked about satellites, but of course now there's a lot of drones and devices like that in the air, in the sky, on obviously military grade, not just the ones that you connect to your phone to do a bit of just peeking on your neighbour's garden. But we're talking about something a bit more industrial. So tell us about the information that you're able to get from the various drones and the various other things that are in the air, I guess, in the atmosphere, in the higher altitudes around the Earth these days.
Right. Okay. We first got involved with drones with this project with Swedish colleagues that I mentioned, the Forest Safe project, because it turned out that in their lunch break, the scientists at the university up at Umeå, they went flying drones. In fact, they got us to build little drones themselves. They put cameras on them, and they put little trackers on, so if they lost them. And so some of that team actually ended up setting up their own company to actually build drones that were specifically built for looking at forest resources, so that they could fly drones that were small enough and light enough that they didn't require a lot of expensive certification like an aircraft. And that business has taken off considerably. And then on the other hand, you've had the really high altitude drones, and NASA actually have a couple of these that are almost if you like, military grade drones, but allow them to fly stratospheric missions, if you like, from California right up over the North Pole and back again, gathering data in a way that would be very uncomfortable for a civilian flight and extremely expensive. And of course, if you want to gather data very close to the ocean surface, that would be incredibly dangerous with a manned plane. So there are real important applications of drones from a safety perspective. And from my perspective, one of the things that's really interesting is both the fact that there's an opportunity to build better technology, not just, most drones are just almost just red, green, blue, just standard color pictures. But if you can actually build like the infrared or the really important spectral data as well, then you can gather data on a drone at a resolution that you could never get from a satellite. So it's this question of, we can actually look at the scale of the plant, the individual plant, that you cannot see from space. And it fills in a gap in our knowledge that the only way of doing that before would be from aircraft, but of course that's an expensive process that requires a considerable amount of funding. And middle part of my career, I was on the airborne steering panel. I was chair of that for the National Environment Research Council. And I know it was an expensive process, and eventually some of those aircraft couldn't be sustained in terms of the cost. And drones have largely filled that gap now, actually, which is good. And a lot of universities have been able to invest in this. It's been relatively cheap. And of course, it allows us to gather important knowledge. So if we're thinking about plant stress, for example, would be a good example. Or it could be you're just wanting to look at what's happening even on a cloudy day, where you can fly under the clouds, where you still get enough energy to take pictures, but a space it would be obscured actually by cloud cover. So I think this is a really exciting time, and I think we're going to see with miniaturization, with better technology, a lot of that. While people might be concerned about some of the military aspects of drones we hear about in the news, there are really important civilian applications. Things like sort of, say, firefighting would be a good example. Going, we talked about mangroves earlier, going into places that are really difficult or actually could be quite dangerous actually to go into, and to gather really good data. So it's like an equivalent of field work. So one of my colleagues calls this air truthing. So instead we think about ground truthing, actually working out what's actually on the ground that we can see from space, we can almost get that equivalent data from a drone. I'll call it air truthing. It's a whole new vocabulary. It's a whole new phrase, if you like.
And a lot of what we've talked about is stuff we're familiar with, and there's quite a lot of legacy stuff there in terms of using old data from satellites. You're in the area, you could, obviously remote sensing is the official name of it that's covering all of this. What is the future then? What does the future hold for remote sensing, be that through satellites or other devices that you talked about there, nanotechnology and so on? What does the future hold in this if we come back in 10 years or more from now?
Well, one of the things that always strikes me is that when I'm teaching my undergraduate course in remote sensing, I've never been able to give the same set of lectures twice, because the technology moves on so fast. There's always a new satellite, there's something happening. You have to update what you've been talking about before. And one of the things that's really very striking is the fact that in the past, satellites that we used were in what was called a polar orbit. So they might be about 980 kilometers up, and they were going, if you like, more or less around the poles while the Earth is rotating round. And so there's a revisit time. So the Landsat Programme I talked about in 1972 had an 18-day revisit time, and then that improved to 16 days. But a lot can happen in 16 days. And one of the things that's been happening, of course, the European Space Agency have launched their own Sentinel satellites, so there are more satellites available, which helps. But also, the satellites can now be tilted to look back and forward so that they're dynamic. And that allows things like that, gets you down to about 4 days. But the other thing that's happening with the CubeSats and nanosats is there are more of them. There's these swarms of satellites. And so it's now possible to have satellite data on a daily basis. So we literally can monitor the planet on a daily basis. Now, okay, there's the cloud cover problem, but nevertheless, that is very, very helpful. So what we can now do is by gathering this data and throwing away, if you like, the clouds, it's possible to get cloud-free imagery much, much more easily. And this data is now being put into what we, if you like, call the cloud that's accessible through the internet. And so with technology just through, if you like, through a programmable browser, we can now access data from almost any part of the world with only a couple of days delay. And then that's just going to improve and improve. And the resolution of those satellites is now getting, as I mentioned, from 30 centimeters. Now, that's not available everywhere, but that is almost certainly the future. We will have a much more monitored planet. It will be much more accessible to a wider range of people. So we'll have our undergraduate students will be able to almost do global change projects in a way they could never have done. When we look at like the journals of remote sensing sitting behind me, there are lots and lots of, if you like, case study papers. We've done a project on this place, but it's a relatively small place. What does it mean for other parts of the world? But it's now possible to do this at regional, continental, even global scale. And I think that will, it's not quite there yet, but I think in 10 years' time, we will have a much more monitored planet. The data sets will be much more easily accessible. We'll be able to use, if you like, the talent from the young people coming forward with some interesting computing skills, and they'll really be able to take advantage and not have to worry so much about the technology, although we need the people building that improved technology as well. I mean, that does have some implications for, if you like, what about all this space junk? And we might want to talk about that as well. You know, what happens to this stuff? Is it just going to be an endless launching of satellites?
Yeah, I was going to say, you know, we talk about the future, but of course we have to make sure the future is sustainable. And that is a growing concern in the space community, is the sustainability of particular orbits, particularly low Earth orbit, of course. And now we've got commercial players in space. There are just so many more satellites going up so much more frequently. And I mean, what are your thoughts on that, I suppose? It is very broad, but do you think that at some point we need to have a sit down of everyone in the space industry and say, look, we need a more measured approach to this. We can't just keep on launching and launching and launching.
What I would say is, if like when I started my career, I would have in my head and be able to articulate to my students the names of all the satellites used for Earth observation. And the thing that's really changed is the fact that we've got these constellations of satellites now. Certainly the major space agencies do have a high degree of responsibility, and we do actually know when these satellites are brought down, because they know, when they will run out of fuel and when this is happening. So there's quite a lot of information on this. So I'm not the person really to sort of comment in detail on this, but I think this is, if you like, where the multidisciplinarity is. I think there needs to be a strong ethical component. I think it's important, actually, that things like space law and space ethics actually become almost like part of our curriculum, that we actually inform people. One of my mentors when I first started was a chap called Professor Ray Harris, actually, who then went on to write the first book on space law. And we kind of need actually more, I'm not sure how many editions that book's gone into, but actually it's getting more and more complicated. And one of the difficulties is that people in the application side, like me, can't keep up with this at all. So we have a sense that we don't just want to be using data sets unethically. That would be a bad thing just because they're cheap, because we don't want this to be totally market driven, because it's important that these data sets are also used and they're actually of benefit. We talked earlier about the benefits to the planet. It's important that those really are beneficial, and the if you like, they outweigh some of the difficulties. But some of the smaller satellite constellations are relatively small objects. I mean, the very first things like the Landsat satellites and the MODIS satellites, they're about the size of a London bus. They're pretty big things. Now, okay, I'm sure they're quite easy to track, but there's a huge responsibility when you bring that down, that you brought it down somewhere safely and that's well away from people.
Thanks for joining us on the podcast this time. It's been fascinating hearing about your side of work, really, and how space can help contribute to our lives and a more sustainable life for us as well here on Earth, keeping an eye on the various changes that the Earth is undergoing. Just finally, if anybody wants to find out more information about the field of remote sensing, or you yourself, how should they go about that?
Right. Okay. So in terms of getting in contact with us, we have our web pages in the Department of Geography at Durham University, and as I said earlier, there are things like the Institute of Data Science, where there are lots of colleagues in many departments who are interested in various aspects of remote sensing. There's, if people are interested, there's also a Remote Sensing and Photogrammetry Society. That is, it's a sort of UK based, but actually has a strong international focus, and they have junior members as well. And so if people are just interested in looking them up, sort of rspsoc.org.uk, that might be a way of just finding out a little bit more about the topic in general.
Okay, well, thanks for joining us, and maybe see you up at Kielder Observatory soon to do some remote sensing of space.
Yeah,
the other way around.
Yeah, I mean, it's. I spent many sort of months looking at Kielder Forest, and so it's really quite nice to have that sort of link back to the Kielder Observatory. It's that's really fun. So thank you very much. I've enjoyed talking to you.
Goes full circle. Thanks a lot. Our thanks once again to Professor Danny Donoghue from Durham University, and explaining more about the work going on in space to protect us here on Earth. Now, online, kielderobservatory.org is the place to go to find out about everything to do with Kielder Observatory, not least to book for our upcoming events. And you can book far into the future as well. In fact, the next year is available online at kielderobservatory.org, so plan ahead, as far ahead as you like, as long as it's in the next year, up to the end of August 2025, on sale at the moment of recording this. So book in advance, and we hope to see you soon as the nights start to get darker. Of course, there will be some great sessions coming up at Kielder, so as Dan Pye has mentioned in previous episodes, this time of year, August, September, start of October, a fantastic time for stargazing. So get yourself online, book one of the upcoming events, and we hope to see you in person soon. And also don't forget to check out some of our previous episodes. There's a lot of them covering all sorts of different topics, from the moon and Mars and the sun, right through to black holes, dark matter, and the search for aliens. It's all covered in previous episodes of the Kielder Observatory podcast. We're back with another episode next month, and we'll speak to you then. In the meantime, take care, and of course, happy stargazing.